I'm excited to dive into the two-pointer technique with you today. It's a powerful strategy for solving array and string problems efficiently, and by the end of this session, you'll be ready to tackle these problems like a pro. We'll keep it fun, clear, and engaging. Ready? Let's get started. Picture you and I searching for a book on a sorted bookshelf. I start at the left end, you start at the right, and we move toward each other, checking books as we go. That's the two-pointer technique. Two markers, or pointers, moving across an array to find a solution. We're a team, working from opposite ends or side by side to solve the problem. The two-pointer technique uses two pointers. Think of them as two variables, or markers, that traverse an array to solve a problem. It's especially useful for sorted arrays or when you need to compare elements efficiently. It reduces time complexity from O of n squared to O of n in many problems. To give you a clear picture of how it works, let's start with a visualization of the technique applied to a classic problem, finding two numbers in a sorted array that add up to a target sum. Let's visualize the two-pointer technique. Given a sorted array of numbers, for example, 1, 3, 5, 8, 12, 15, 18, 22, 27, 30, and a target sum, for example, 40, find a pair of numbers in the array that add up to the target sum. Return the pair if it exists, or indicate if no such pair is found. For example, in the array with target 40, check if there are two numbers whose sum is 40. The video demonstrates the technique on a sorted array: 1, 3, 5, 8, 12, 15, 18, 22, 27, 30, with a target sum of 40. Start. Left at index 0, value 1, right at index 9, value 30. Sum equals 1 plus 30 equals 31. Too small, move left to index 1. Step 1. Left at index 1, value 3, right at index 9, value 30. Sum equals 3 plus 30 equals 33. Too small, move left to index 2. Step 2. Left at index 2, value 5, right at index 9, value 30. Sum equals 5 plus 30 equals 35. Too small, move left to index 3. Step 3. Left at index 3, value 8, right at index 9, value 30. Sum equals 8 plus 30 equals 38. Too small, move left to index 4. Step 4. Left at index 4, value 12, right at index 9, value 30. Sum equals 12 plus 30 equals 42. Too large, move right to index 8. Step 5. Left at index 4, value 12, right at index 8, value 27. Sum equals 12 plus 27 equals 39. Too small, move left to index 5. Step 6. Left at index 5, value 15, right at index 8, value 27. Sum equals 15 plus 27 equals 42. Too large, move right to index 7. Step 7. Left at index 5, value 15, right at index 7, value 22. Sum equals 15 plus 22 equals 37. Too small, move left to index 6. Step 8. Left at index 6, value 18, right at index 7, value 22. Sum equals 18 plus 22 equals 40. Target found. Stop at 18 and 22. The video shows how the two pointers converge, moving based on whether the sum is too large or too small, until they find the target or meet. This visual sets the stage for understanding how we'll apply the technique to specific problems. Problem 1. Check if an array is sorted. Given an array of integers, determine if it is sorted in non-decreasing order, meaning each number is at least as large as the one before it. For example, the array 1, 3, 5, 7, 8, 10, 12, 15 should return true, while 1, 3, 2, 7 should return false. A basic approach is to iterate through the array and compare each element with the next one. For the array 1, 3, 5, 7, 8, 10, 12, 15, we'd check, is 1 less than or equal to 3? Yes. Is 3 less than or equal to 5? Yes. Is 5 less than or equal to 7? Yes. Is 7 less than or equal to 8? Yes. Is 8 less than or equal to 10? Yes. Is 10 less than or equal to 12? Yes. Is 12 less than or equal to 15? Yes. If any comparison fails, the array is not sorted. If all pass, it is sorted. Time complexity, O of n, where n is the array length, as we make one pass through the array, checking n-1 pairs. Space complexity, O of 1, as we only use a constant amount of extra space, a loop variable. With 2 pointers, we use 2 indices. Left starts at the beginning, and right starts one step ahead. For the array 1, 3, 5, 7, 8, 10, 12, 15, step 1. Left at index 0, value 1. Right at index 1, value 3. Check. Is 1 less than or equal to 3? Yes. Move left to index 1, value 3. Right to index 2, value 5. Step 2. Check. Is 3 less than or equal to 5? Yes. Move left to index 2, value 5. Right to index 3, value 7. Step 3. Check. Is 5 less than or equal to 7? Yes. Move left to index 3, value 7. Right to index 4, value 8. Step 4. Check. Is 7 less than or equal to 8? Yes. Move left to index 4, value 8. Right to index 5, value 10. Step 5. Check. Is 8 less than or equal to 10? Yes. Move left to index 5, value 10. Right to index 6, value 12. Step 6. Check. Is 10 less than or equal to 12? Yes. Move left to index 6, value 12. Right to index 7, value 15. Step 7. Check. Is 12 less than or equal to 15? Yes. Move left to index 7, value 15. Right to index 8, out of bounds. Stop. If any check fails, like in 1, 3, 5, 2, 8, 10, 12, 15, where 5 is greater than 2 at left equals 2, right equals 3, we conclude it's not sorted. Time complexity, O of n, as we still make one pass through the array, checking each pair once. Space complexity, O of 1, using only 2 pointers regardless of array size. The 2-pointer approach is conceptually clearer, as it explicitly tracks the pair being compared, but the complexity remains the same as the simple method. Problem 2. Find a pair with a given difference in a sorted array. Given a sorted array of integers and a target difference, find 2 numbers whose difference, larger minus smaller, equals the target. Return their indices if found, or indicate no solution exists. For example, in the array 1, 3, 5, 8, 12, 15, 18, 22, 27, 30, find 2 numbers with a difference of 7. A brute force approach checks every possible pair of numbers. For 1, 3, 5, 8, 12, 15, 18, 22, 27, 30, we try pairs like 3 minus 1 equals 2, 5 minus 1 equals 4, 8 minus 1 equals 7. Found. Indices 3, 0, 12 minus 1 equals 11, 15 minus 1 equals 14, 18 minus 1 equals 17, 22 minus 1 equals 21, 27 minus 1 equals 26, 30 minus 1 equals 29, 5 minus 3 equals 2, 8 minus 3 equals 5, and continuing through all pairs. This finds 8 minus 1 equals 7, but it's inefficient, checking many unnecessary pairs. Time complexity, O of n squared, as we check each element against every other element, resulting in n times n minus 1 divided by 2 comparisons. Space complexity, O of 1, as we only use a constant amount of extra space, variables for indices and differences. Since the array is sorted, we use 2 pointers, left at the beginning, right starting ahead. For 1, 3, 5, 8, 12, 15, 18, 22, 27, 30, and target difference 7. Start. Left at index 0, value 1. Right at index 1, value 3. Difference equals 3 minus 1 equals 2. Too small. Move right to index 2. Step 1. Left at index 0, value 1. Right at index 2, value 5. Difference equals 5 minus 1 equals 4. Too small. Move right to index 3. Step 2. Left at index 0, value 1. Right at index 3, value 8. Difference equals 8 minus 1 equals 7. Target found. Return indices 3, 0. If the difference were too large, move left forward. If too small, move right forward. If no pair is found, the pointers exhaust the array, indicating no solution. For example, if the target difference were 10, left at index 0, value 1. Right at index 4, value 12. Difference equals 12 minus 1 equals 11. Too large, move left to index 1. Left at index 1, value 3. Right at index 4, value 12. Difference equals 12 minus 3 equals 9. Too small, move right to index 5. Continue until pointers meet or cross, indicating no solution. Time complexity, O of n, as each pointer moves at most n times, traversing the array once. Space complexity, O of 1, using only 2 pointers and a few variables. The two-pointer approach is much faster, leveraging the sorted array to efficiently narrow down the search. Here are some quick tips to master the two-pointer technique. Sorted arrays. Two-pointers are most effective with sorted arrays. Check if the problem provides a sorted array or requires sorting, which adds O of n log n time. Problem-solving mindset. When stuck, ask, could 2 pointers, one starting here, one there, help me find the answer faster? Practice. Try problems like reversing a string or finding a subarray with a given sum to build confidence. That's it. You've learned the two-pointer technique, starting with a visualization and applied it to checking if an array is sorted and finding a pair that sums to a target. With complexity analysis, you understand the efficiency gains. You're ready to tackle similar problems, and I know you'll crush it. Thanks for learning with me. Let's keep sharpening those coding skills.